Okay, another fluoride compound, another tetrafluoride. We have four fluorines, but this time instead of silicon, Si, we've got sulfur. And silicon is over here with its four valence electrons, uh, making four bonds typically. But the sulfur has six valence electrons, two more. You'd expect to have two bonds, but sulfur is third energy level, so it can end up using its d orbitals for even more bonds, but we'll get to that in a second. So sulfur, six electrons, fluorine, 7 times 4, 28. We do our usual routine, and we find out we have two extra electrons. Our original Lewis dot diagram with the silicon had, of course, these four fluorines with their octets, their extra 26 electrons, but we have two extra electrons that we've got to find a room for, and that goes into the central atom. So I'm going to move it. I'm going to take these two electrons, and there's a spot here I can sort of squeeze them in, but the problem is we've got a two-dimensional drawing, and this is sort of really not how it happens. This would be the correct Lewis dot diagram for the sulfur tetrafluoride, and we would give it 1, 2, 3, 4, 5 valence electrons. Excuse me, a steric number of 5, 4 bonds, and 1 unshared pair. So let's go to that shape table again. Right here, we've got a steric number of 5 because we have to deal with 5 sets of repulsions. In this case, it's going to be 4 bonds and 1 lone pair right here. This would be the shape. If we had bonds all around here, a sulfur pentafluoride, which I don't think forms, it'd be trigonal by a pyramidal. But this is called a distorted tetrahedron, which is a mouthful, so usually it's called seesaw. It's sort of funny using that term seesaw, but there's all sorts of analogies in organic chemistry. They've got a molecule that they refer to as the lawn chair configuration and the boat configuration, and we may deal with those a little bit later when we do organics. So let's look at the diagram. Here we go. This is going to be the shape of our sulfur tetrafluoride and seesaw I'll do the seesaw later. And the bond angles are going to be different. We've got our axial bond angles that are 120, and then we've got these. So you've got both 120 and 90 degrees involved in here. So far, the AP exam hasn't asked about those different angles, but they would expect that you would know that this is an unsymmetrical molecule and it's got a cloud of electrons. Let me flatten this, and let's deal with the electronegativity differences. We still have got a big electronegativity difference. Fluorine at 4 and sulfur at 2.5. Not as bad as the fluorine and silicon. But the thing is that we've got a different geometry. We've got a fluorine pulling in this direction, a fluorine pulling in this direction, which those will cancel. But we've got a couple pulling down, and they're pulling down in the same direction. And this cloud of electrons isn't going to be pulling on anything. In fact, it's out there all by itself. So this is definitely unsymmetrical. And with these two fluorines pulling down, this definitely has a dipole. This is a unsymmetrical molecule that has a negative side, which will undoubtedly be here, where we've got our two fluorines pulling together, and a positive side, my guess would be on this top area. Even though there's a cloud of electrons, those electrons don't have as much of a say in things as here. So there's a definite dipole, and there's good reason you can experimentally find the dipole, but also remember the silicon tetrafluoride had a boiling temperature of like 100 degrees below zero, which is not unusual for symmetrical molecules. Usually they're gases at room temperature. But if you get a dipole, these little positive and negatives make molecules stick to one another. And the boiling point of this substance, sulfur tetrafluoride, is like negative 38 degrees below zero, 70 degrees warmer. And you still have the same number of fluorines. It's this dipole that makes all the difference in the world. To see the shape a little bit better, I put this here, and this ball and stick diagram maybe is a little bit better for showing the, let me try a little seesaw, or if you like long words, distorted tetrahedron. I'm not sure you even like the distorted tetrahedron because it's really not a tetrahedron anymore. But it does have tetra bonds, it has 4 bonds. And we've got our dipole. And one extra little thing, this cloud of electrons is a bit repulsive again. So the angles will not be the 120 that we actually expect. We actually get down to 102. But I'm pretty sure they wouldn't deal with that. So the expected is 120 and 90. So here's the actual data for the molecule. So there's another one of our 4 fluorines, but this time with the sulfur.